get to the next question is actually quite related to this one. Can information be destroyed? And the answer to this is it depends. And I go on to explain exactly what it depends on. So if you think about what you learned about physics in school, maybe Newton's law, you have an arrow and the initial position and the initial velocity of the arrow, then you can calculate exactly where the arrow will land. This is an example of natural law that we're all familiar with, but actually all the natural laws that we use in the foundations of physics work exactly the same way. We have some initial state, then we have an equation which is called an evolution law, and from this we calculate a final state. We can also do this backwards. So if you know where the arrow landed and what the velocity was by which it landed, you can calculate where it came from. So those time evolutions that we have, they're all time reversible, at least in principle. So when I say time reversible, I just mean you can use this law forward and backwards. Of course, in practice, a lot of things are not time reversible just because they're really, really difficult. Like if you're mixing batter, for example, it becomes so difficult so quickly that you cannot, in practice, ever actually figure out what the initial state was from the final state. But in principle, again, this is theoretical physics, you could, if you knew exactly where all the single molecules are located in your bowl, you could figure out what the initial state was. Okay, so I asked the question like, can information be destroyed? Well, we have to talk about what do we mean by information. What I mean by information here is just all the data that you need to specify the initial state. And what happens in all those evolution laws is that the information is reconfigured, but it can never get destroyed, because in principle you could always take the final state and apply your evolution law and figure out exactly how it started. This is another reason why the past still exists in some way. You just rearrange things in the universe, you never actually destroy them. So so I said this is all fundamental laws, except there are two things which don't fit in this pattern. So in quantum mechanics, we do have an evolution law which is time reversible. That's called the Schrödinger equation, and we can use this forwards and backwards. But this isn't the only thing that's going on in quantum mechanics. In quantum mechanics, we have a second ingredient to what happens in the universe, which is the measurement update. So quantum mechanics, everything is described by what's called a wave function. So there's a wave function for everything, for electrons, for atoms and molecules, but also for you and I, and in principle for the entire universe. So we describe everything by this thing that's called the wave function, but the wave function itself is not observable. It's just a device to calculate probabilities. And so what happens when you actually make a measurement on a single particle, suppose you have the left probability distribution for an electron or something, the moment you measure the electron, you know where it is. So suddenly you know with 100% probability where the electron is, which means you have to update your wave function the moment you make a measurement. Now, the problem with this is that once you have made the measurement, you no longer know what the wave function is that it came from. Could have been anything. Maybe the 100% were peaked with 60%, or maybe it was just 20% and you just got lucky. There's no way of telling. So this measurement process is irreversible. You cannot tell from the final state what the initial state was. This is one reason why information could actually get destroyed. So you can't figure out what the initial state was. Measurements in quantum mechanics do destroy information if you think that the theory, that the way that we currently use it, is actually fundamentally correct. And there are some reasons to doubt this. One of the major clues that maybe quantum mechanics isn't the final story is that it requires you to talk about detectors to begin with. If quantum mechanics was really a theory for the fundamental constituents of matter, then it should explain what a detector does. You should be able to calculate it. Instead, quantum mechanics has to assume that you know what a detector is. And that's certainly true to some extent in practice. We know a detector when we see it, but the theory doesn't explain it. And so I think this is the clue that quantum mechanics isn't fundamentally the right thing. And there's also the question, like, if we have a wave function for the entire universe, well, who measures this? There's no one to measure it. Those, I think, are reasons to be kind of skeptical that the measurement update is actually the right description of the physical process. But as I said, I'd warn you if this is speculation. This is just speculation. Okay, so the other process which might actually destroy information is black hole evaporation. So normally, the way that black holes are introduced is if you throw something in, it can't come out. So it's forever hidden behind the horizon. So you could say, well, if I take a book and I throw it into a black hole, then it's gone. But that's not necessarily a problem, because just because you can't access some information doesn't mean it's been destroyed. If I take a book and I lock it into a chest or something, you can also no longer access it, but you wouldn't say that the information has been destroyed. So you could say maybe the same is going on with black holes. But then in the 1970s, Stephen Hawking came and said, well, the black holes don't sit there forever, but they evaporate. They emit what's now called Hawking radiation, which is basically completely random radiation, contains all the particles that we know of in different fractions. And the important thing is that this radiation contains no information other than the mass of the black hole, but very few bits, so to speak. And it carries away energy from the black hole, and the entire energy is conserved. So what happens is that the black hole shrinks, and it radiates and it shrinks, and eventually it's entirely gone. The only thing that's left is a lot of this Hawking radiation, which doesn't contain any information. So if you've thrown in your book into the black hole, the information really gets destroyed. It's a process that's not reversible. And there are lots of problems with this. One is that if you just take this process of black hole evaporation, it's inconsistent with quantum mechanics even before you make a measurement. Because as I told you, the time evolution in quantum mechanics, the Schrödinger equation is reversible. Yet the time evolution of black hole evaporation is inconsistent with this reversibility. So something doesn't match up. And then after this, maybe you make a measurement, but the problem occurs already before this. This is the reason why most physicists currently believe that something is missing in Hawking's calculation. For example, this calculation doesn't contain anything about the quantum properties of space and time itself. That's because we don't have a theory for the quantum properties of space and time. That's normally called quantum gravity, so that's not in the calculation. That may be a reason why the result isn't correct. There are lots of other solutions physicists have put forward that I don't want to go through, but that'll be another 2 hours or something. But the bottom line is that we don't know. We believe there's something wrong with this calculation. Hawking himself actually changed his mind. He originally thought information is actually destroyed in black hole evaporation, but later in his life changed his mind and thought that actually it comes out at some point. But we can't experimentally test it. The reason is that the black holes that we actually know exist out there in the universe, they're very massive, and the Hawking temperature is inversely proportional to the mass. So the heavier the black hole, the smaller the temperature. And the temperature of all those black holes is so small that we can't measure it. It takes them hundreds of billions of years to evaporate. So we can't experimentally test it, and the bottom line is we don't know. So the answer to the question, can information get destroyed, depends on what you believe happens in a measurement in quantum mechanics and in black hole evaporation. Personally, I think the answer is no. I think really fundamentally those two processes are time reversible. So then let's talk about the question: how did the universe begin? Where do we all come from? And if you read any popular science news about physics at all, you've probably heard countless different stories about this. My brief answer is we don't know. And I'll try to explain why I say this. So the way that modern cosmology works is that we use Einstein's equations for general relativity. So those equations, to make a long story short, they explain how space-time behaves in reaction to the distribution of matter. In particular, this theory tells us that the universe expands. You've probably all heard of this. We've also figured out that not only does it expand, the expansion actually gets faster. And the rate of expansion is determined by the amount of matter and energy in the universe. And so the other way around, you can measure the expansion, you can infer what has to be in the universe. And this theory makes a lot of predictions. For example, the formation of structures, their pace and the distribution, the cosmic microwave background and the properties of the cosmic microwave background, the abundances of the lighter atoms, a redshift of distant galaxies, etc., and etc. So this theory, which we have for the universe from Einstein's theory of general relativity, is pretty good, and physicists are quite happy with it. It has a little problem, which is if you take those equations and you extrapolate them back in time, well, as I just said, the universe currently expands, so if you go back in time, then everything gets closer together and the density of matter increases and increases, and eventually it'll be infinitely large. That's a singularity. It's not only the energy density that becomes infinitely large, but also the curvature of space. And it happens at a finite time, at about 13.7 billion years before now. And this is called the Big Bang. Actually, I should probably add that physicists, pretty much no one believes that there was actually a singularity at the Big Bang, but it's probably just a sign that the equations break down at some point. So physicists use the word Big Bang to refer to whatever it'll be that replaces the singularity. But now remember how natural laws work. As I told you earlier, you have an initial state, you have an evolution law, and you get to a final state. Now, this brings up the following problem. Suppose you make a measurement for your final state, as we do in cosmology. So we have a measurement right now. We have an idea how the universe looks right now. Then we have an evolution law, and the evolution law gives us an initial state. So we work back in time. This is exactly what we do if we want to explain what happened in the early universe. Well, the issue is that you can take any evolution law, and it'll give you an initial state. And then if you take this initial state and you apply the evolution law to it, that'll correctly give you what we observe today. So how do we ever know which law is the right law if there's always some initial state that you can construct from our observations? Well, the answer is that this evolution law, together with the initial state, has to actually explain what we observe. It has to be a simple story to some extent. It's basically Occam's razor. So if you think about what I told you earlier, all the things that modern cosmology explains, like the cosmic microwave background and the structures and so on, those all come out of a simple initial state. And the theory actually tells you how those different things belong together, like how the formation of structures and distribution of galaxies and their correlations and so on hang together with the properties of the cosmic microwave background. This doesn't work for any initial state. Generically, you'd have to put a lot of information in the initial state so it wouldn't be simple anymore. So what this tells us is that the key justification for using a theory for the evolution of the universe is that it has to be simple. It has to be a simple explanation for the observations that we have today.